Hello, my name is Omari Hitson, and I'm going to be presenting to you my Lab 2 concerning an object in freefall motion. The prompt of this lab was to observe an object in freefall motion in order to create an observation model as well as a computer model that accurately predicts the future position of the object. We then compared these two in order to answer the question if a thrown object would exhibit similar motion to that of the observed object in our video. In order to answer this question, we're going to need to identify the components of the terminal velocity, understand what terminal velocity is in the first place, and identify the forces that are acting on the object in order to more accurately predict the object's motion. The knowledge acquired in this lab is particularly valuable because being able to accurately describe an object's motion allows for a more accurate prediction of that same object's motion in the future. This would be particularly important if you were considering safety precautions and preparations when skydiving, or similar safety precautions and preparations when bungee jumping. Several basic concepts will be reiterated throughout this experimentation. Firstly, Newton's first law, which says an object at rest will stay at rest, while an object in motion will stay in motion unless it acted upon by an outside force. Next, we're going to be using a lot of Newton's second law, which we will derive several other equations from. The original equation, force is equal to mass times acceleration. Lastly, we're going to use the concept of terminal velocity and drag force in order to create a free body diagram that helps us to more accurately describe the motion of the object in question. Two very important values that we'll be inputting into some of the equations that you'll see later on is the mass of the paper ball, which comes out to be 0.028 kilograms, and the acceleration due to gravity, which is negative 9.8 meters per second squared. Similarly, it'll be quite important to identify our system versus our surroundings. In this particular experiment, we're identifying the paper ball as the system, and the force of gravity, as well as the drag force, being the surroundings. Next, you'll notice a similar diagram to that which was just shown to you. Here, this blue circle is representative of the paper ball. Above it, you can see the force of the drag, which is opposite the force of motion, and the force of gravity, which is acting on the force downwards. We're going to utilize Newton's second law in order to derive several things about these two forces. Firstly, we understand that the net force is equal to the force of the drag plus the force of the gravity. This is equal to the net force in the y direction. Extrapolating on that, we'll find that the force of gravity is equal to the mass times the gravity, which we've identified already as negative 9.8 meters per second squared. Next, you'll notice the drag. This drag equation is shown here, but what's important to us is that extrapolating on that, we'll find that the force of gravity is equal to the mass times the acceleration due to gravity. We already know this and identified it to be negative 9.8 meters per second squared. Next, we need to identify the force of the drag, which is actually quite simple using the equation that we have here. But instead of using the entirety of the equation, we can derive that the first letters before the v is all one constant, which we can then simplify to negative v times v. Here, we're taking an empirical observation of the ball being dropped, putting it into tracker, tracing each point, and then coming up with a time versus position plot. That same plot was shown to you previously, and is shown here again. Next, we need to make a computational model that is very similar to the empirical model which we just observed. So, firstly, we have to input a couple of things. We'll start with our initial conditions, which we'll take from the empirical observation that we already made, which is the y component at the first initial time that we've already put in. Next, we'll tell the code how long of a duration we want to observe this ball, which can be found by the final time observed in our empirical observation. In this particular computational model, we're going to account for gravity. In order to do so, we need to input the force of the gravity. So we do so by the mass times the acceleration due to gravity. We then input the equation in order to derive the next velocity and the next position for it to predict. We can derive this from the Newton's second law equation that we showed earlier, F is equal to ma. But we can switch it around because we need to find the acceleration. We know what the force is and we know what the mass is, so we input this into the computation as well. The result of this is the diagram shown, as well as the plot which shows the position versus time. Comparing this with the data that we saw in our empirical experimentation, we see that this computational model overshoots the position. In order to make this more accurate, we need to take into account all of the forces acting on this paper ball. In order to do so, we also need to include the drag acting on the ball. Since we're able to calculate the velocity, all we need to do now is to find a proper b. In order to find this b, we go through a series of trial and error inputting this until we get a similar final position in the computation model to that we observed in the empirical model earlier. Finally, this is what we get when we input both the force of the gravity and the force of drag. Putting these two together takes into account all of the forces that are enacting on the paper ball and makes our computation more accurate. By putting these all side by side, we're able to see what happens when the experiment takes into account only gravity, when it takes into account both gravity and drag, and our empirical observation that we saw earlier. Finally, we can conclude that accounting for both the gravity and the drag force made for a more accurate model. We can also conclude that the empirical data could have been more accurate if we dropped the ball and started the initial observation at the same time. However, this was not the case. So finally, we arrive at the question that we asked originally: which models can predict terminal velocity?